There you go. I see some thumbs
Hello.
up. All right. Good, good. I was just making sure everything was working the way it was supposed to. All right. So today we're going to be talking about pointers in C++. Um, I am going to start this off with a bit of a disclaimer. Uh, Actually, a couple of disclaimers. Number one, this will probably be the most difficult thing that you have to do in C++. Um, Working with pointers can get very confusing, um, to the point of I get confused, and I am not embarrassed to admit that. Uh, Unless you just do it all the time, this is why a lot of people hate C++, because it requires the developer to be hyper focused, for lack of a better term, to really understand and know what's going on and to keep track of what's going on. If you don't, there are easy ways for you to get what they call memory leaks, which is where um, uh, this is kind of like a subset of pointers where basically you create objects, they get put out there, and you start referencing other objects, and you forget that you ever did the first one, and so your memory starts being slowly consumed as your program runs longer and longer and longer because you forgot to release that data. It's also very easy to accidentally point to the wrong part of memory because pointers is all about pointing to locations in memory. Um, and that means that you can kind of blow stuff up without trying. Point to something relatively low in the memory stack, and it's a problem. Now, with that being said, uh, two very important things. One is with modern operating systems, um, Windows 7 was a big start of this, if I remember correctly. Might have been a little bit before, and each version of Windows is getting better. Um, One of the things that they did is they removed what they called shared memory space. Um, Shared memory space is just a horrible, horrible, horrible thing to deal with. Um, it was a source of a lot of developers' problems. And shared memory space was the idea of you have memory, and memory is memory, and that meant that you could accidentally step on someone else's memory. So if you had 2 or 3 programs running or a dozen programs running, um, it would be very easy for you to pick the wrong variable or wrong memory address to start referencing because you just you didn't pick the right thing. And stuff that was in low memory, so if we think of our memory kind of nice along this way, a little bit easier to see. Stuff that's down here on our far left hand side, um, that would be what we consider low memory, and that would be where things like your operating system ran. And that would tend to be where all new developers tended to crash their applications. Because what would happen is instead of referencing a memory location, you would reference the variable value, and the variable value might be something like 103. Well, 103 in hexadecimal is on that very low end scale where your operating system is going to reside. Your application resides over here. You're over here, and it will blow stuff up. And this was notorious for things like if you're running back in the old days of DOS or even early Windows versions, because um, a lot of the early Windows versions had a lot of backwards compatibility with a lot of DOS stuff, which it needed to have those other applications still run. The flip side or bad side to that was that you could just easily crash your whole system. Uh, so if you remember seeing things like the old blue screen of death, um, an often cause for that, especially early on, was one application talking to a piece of memory that either didn't exist anymore, or it belonged to someone else. Now, with the modern operating systems, what they've started doing is saying the operating system controls a lot of memory management for you. This makes their job a lot harder, but our job a lot easier. So now when you go to run an application, you get your own segmented space of memory. It still might be out here in the, if you look at your totality of memory, it still might be here. But to your application, it only sees this part. It can't go outside of this little segment of memory. And because it can't go outside the segment of memory, the odds of you touching something else and crashing it or crashing your whole operating system is much, much lower. You might crash your application, that one application. Don't get me wrong. We can still do that. We can do that with ease. But the cascading effect of crashing the entire computer or crashing another application, that goes way, way down. And it doesn't matter if your memory's here or over here. It doesn't matter where it is in that kind of huge matrix of memory that your computer has to store. It's only dealing with it. It's all about just protecting this little piece for you, so you don't have to worry about it. And so that's one of those key things that the new operating systems are doing, which makes learning about pointers a whole lot easier. The second thing I said, I told you two things I wanted to kind of point out that we're going to do, because this is a challenge, is that we're going to go a little slower than normal. If you get it and you're awesome with this, great, more power to you. If not, don't worry about it, because like I said, we're going to go slow. We're going to do some examples. We're going to practice some stuff, and some things you're going to look at and go, why are we doing this? Why? And it doesn't make sense. We'll talk about that type of thing when we get to it. So don't worry about that. But I am going to want to take this just a little bit slower, just to help process and go through the whole situation and get you kind of used to it, for lack of a better term. And then the third thing I said too, I forgot there was a third. The third thing is, and this is really good news, I think, for you as a developer, especially when you're starting out, because it can be frustrating, is that when you go and look at other programming languages, so things like Java or C#, those types of things, they don't have nearly the issues with memory management. And that's because they don't have pointers. It's all handled internally to the to the programming language in conjunction with the operating system. So what that means is, in general, you don't have pointers. You'll have references, and references do basically the same thing. For what most people need to realize, the difference between a reference and a pointer is so small that you don't need to realize it. Now, if you were writing a programming language, if you were writing an operating system and doing the memory management cores, if you were doing some really detailed programming, especially system level stuff, then the difference between a pointer and a reference becomes more important to you. But for the vast majority of people, it's you can call them equivalent, and it's accurate enough. And so that's a real important thing to kind of just put in back of your mind, is once you can get through this, if you're not going to be doing low-level programming, doing programming in C++, you can just kind of go, I'm glad I knew how to do that. Makes me appreciative of what I've got here inside of whatever language you are using, and then you just keep moving forward. So just a couple of quick things to kind of notate about that. Let me pull up my screen. I'm going to start to look at what we're going to be doing. So this chapter is kind of long. It's about 30-something pages, if I remember right. So we're going to break down about half of it today and do the other half next week. Just kind of go step by step through this whole process. We're going to look at 4 major sections. The pointer basics is the largest one. that we're going to look at as far as just understand what the pointer is and what it's going to do. And then we're just going to do some little things to be little tips and tricks and ways to work with stuff that make it a little bit easier for you. So just hold in there with us as we go through this. All right, so thing number one that you need to know, a pointer variable, or sometimes it's just referred to as a pointer. It is a variable that stores a memory address. And this is very similar to any other variable that you store in a memory address. So if you have, for example, int count, string name, double radius, these are all things we've seen before. Those all have a data type and an instance name, or a variable name, if you would. Okay, and the data type is important for a couple of things. It lets the compiler know how much memory needs to be stored for that variable. Okay, so an integer takes up a certain amount of space in memory, a double takes up a different amount of space, and a string is once again another amount. Okay, those are all very important, and they all have a memory address associated with it. So the compiler, when it's running the program or making the program for you to run, it has to keep track of how much space does a variable take, where is it going to be located, and that will sometimes be stored off in my execution runtime, so it keeps track of it. What the link is to the variable name, so it can go and find where the variable name is used throughout and use that memory address to move back and forth. A pointer is very, very similar. The difference is we're going to add a star to the end of our data type. And all pointers talk to a memory address. So a memory address is going to be a fixed size inside of my application. And so you might be going, well, if it's a fixed size, why do I have to give it all these different data types? Why can't I call it like a memory data type? And it just stores it that way. And that's a very good question if you're kind of thinking that in the back of your mind. Because if I'm looking at memory address, I know all memory addresses are 16 bytes or maybe 8 bytes or 2 bytes, depending upon how big my operating system, how much RAM I have and stuff. Why do I care about specifying the data type that my pointer is pointing to? Well, the reason why is the application needs to know when it goes out to this memory address out here, how big a space does it need? Does it need just so much, or does it need this much? How many bytes is it looking for? So not only is it keeping track of where in memory some data is located, it also has to keep track of how much space do I need to be using when I go and grab a value from that location. Because the idea is knowing where the memory location is of a data type is fine. That's no big deal. Being able to extract the information from that location, that's what's really important. That's what we really need to be able to do. In this, you'll notice something else. You'll notice that I put a P in front of all of my variable names. You might be going, why did you do that? That's kind of weird. It's just to make sure that for me as a developer, this is one of those little hints that people have developed over the years to try and figure out how do we make working with variables easier. So especially with pointer variables. One of the things that we do is we'll put a P in front. That way we immediately recognize that this is a pointer variable. I'm not talking about my regular variables. I'm talking about a pointer variable. Excuse me. Now, with that, you'll notice that all of my pointer variables in the little second block of code I have here directly reference a name inside of my first block. And that's just for simplicity's sake. We're referencing them this way. We need both of them. We can't have just one. We need both of them at this point. Where pointers become a lot more powerful is when we start creating data and remembering where it's located and not giving it a name. We're going to do that with objects and complex data types. That's where it becomes a lot more powerful. We're just not there yet. We're taking baby steps to make sure it's easy to go through. So I'm going to come over here real quick. Oops. I have some data. Just let me void this out. Okay. So I've got my first sets of data, and then I'm going to just copy and paste my pointers. Okay. So real simple, real straightforward. If I go and build this, there's no errors with it. It's exactly what you expect. Life is good. Okay. If you were to look at it, you might kind of see down my output that I have some warnings. This is just I've got variables created that I have not instanced or I've not referenced a value to yet, not given any values or anything like that. So no big deal there. Okay. So how am I going to get the value for my pointer? That's the big question. And so let me kind of show you what's going to happen with this. All right, so I'm going to come in here and I'm going to say count equals 10. This way I'll give it some values. Radius equals 4.5. And name is going to be Jean. Okay. So the way I'm going to reference this, I'm going to say p count equals ampersand counts. You might go, wait a second, what's this ampersand for? Okay. So p count is my pointer. I know it's a pointer because I have a star immediately after my data type. This lets me know that I'm using a pointer of type int, so it knows when I go out to my memory address, it gets enough bytes for my integer. And then you're going to say, okay, well, where is that memory address? Well, I need the memory address for count. And a common error is to forget this ampersand. And if I say p count equals count, now the good news is it looks like it's going to give me an error. Some old operatings or some old compilers will go, okay, and let you do that. This was actually used to be a warning, and that was because your integer could store something the size of a memory address. Now it gives you an error. That makes life a little bit more difficult. So I'm going to say, okay, I'm going to use the ampersand. The ampersand says, give me the memory address of my variable, whatever it is. If I go and build this now, boom, it works. Okay. I can do this for all of my variables. So I'm going to say p name equals ampersand name and p radius equals ampersand radius. Okay, so all those work the exact same thing. Does not matter if it's an integer, float, string, nothing. If I say cout p name and do p name like this, I can do cout oops, got my indel there. Don't mind me. Let's take a quick look at what that's going to generate for us. Okay. So p name here on line 19 is saying, give me the memory address of name. Memory address of name is now stored inside of p name. That happens to be 00DFFCBC. Okay. The value of name is John. Okay. That's kind of what we expect. We expect to be John because I see that I assigned that value up here. Now let's see what else we can do with this real quick. If I say ampersand name, this should be the same value as p name because that's what we stored inside of p name, correct? That should make sense, right? And if I look at this, you'll notice that it went off, it created this application, put a different memory location. We have just different memory block to work with. That's fine. That's fine. We see that here in our example. That's what I want to see. Is I want to see that P name and ampersand name, which is the address, is how we get the address and stored in our pointer, works the same. Now you might be going, great, but how? Okay, I know where my address is for this variable, but how do I access that value? Well, I'm gonna put a. Let me double check my sample code. Yep. Oops. Should have that as P name. I knew that didn't look quite right. Remember I said it makes it a little bit harder to keep track of? Good little example of that. All right. So I'm going to get star P name. Now, what does star P name do? Well, star P name is very simple. Star P name says, get me the value of my that is stored at the location where my memory address is. Okay, so I can use ampersand in my regular variable to get my address. I can store this inside of a pointer. Then if I say star in my pointer name, it's going to go out and it's going to do something called dereference. It's going to go out, get the reference location, get the value from it. It's called dereferencing, and it's now going to return that value. So I have access to it. It doesn't matter where this is going to be in my memory. It's going to go out there and it's going to go get that. And you'll notice that, like I said, some of the better things that have come out with some of the more recent versions of C++, if I did star and name instead of P name, notice that it goes, oh, wait a second, this isn't a pointer. And so the compilers, as our computers have gotten stronger and faster and have more memory, can do more things, they've actually become much better at this. And this is useful for other things as well. So for example, if I said p count plus, that might be a problem. Let's take a look at what's going to happen here. Cout, oops. There you go. Okay. Now I say I want to increment cout. Okay, I'm going to increment counts. I'm putting it before and after just so I can kind of see what gets generated. If I go and run, notice that this creates a real problem for me. Okay, and you might go, I didn't give an error. What's the problem? My memory address of where I'm storing, where I'm looking at, has changed. I'm no longer looking at the same memory address. I went from F734 to F738. Why did it jump 4? I only incremented once. Well, it knows it's an integer and it moves to the next integer spot. So it says, okay, let me jump 4 bytes. Now, why is this a problem? Well, let's do this real quick. Real simple. I want to get the value at p count. Okay. So here initially, here's my memory address, F76C. The value stored at that memory address is 10. We're fine. P count has now been updated to F770, 4 bytes further along because we're dealing with an integer. Its value is not right. Okay. this is one of those problems we can run into. We want to update our counter. C++ let us do it. But we did not actually update our counter. We updated where our pointer was looking at. Real problem. Okay, so how do we solve this problem? Well, I can say star p counts. I put in parentheses so I make sure I do the memory dereferencing first, find its value, I increment its value. Now when I run, notice I have F9E7, its value is 10. I then do the star p count inside parentheses plus plus. My memory address is exactly the same as it was before. The value has updated. Okay, so remember I said this, it can be a little bit complicated. Sometimes it's smart enough to catch, sometimes it's not. This is a perfect example. And you might go, well, why didn't it catch that? Why did it let me increment where that value was? That's legitimate C++, and we can actually use that to our advantage if I know I've got a data structure which has sequential elements. You might go, where would that be? Well, it's actually pretty simple if you think about it. Think about where you have a series of sequential data elements that are all the same. And if you say an array, you're correct. Okay? Your array has a starting memory location, and it has a sequence of elements that are accessible to it after that. So if I have a variable, I could have one that starts at a point, and then I could have a variable I just do a little incrementer to move to different elements. In fact, the book talks about this. It has a whole subsection on doing that. Most people do not use arrays like that. We use them as using indexes, but that's actually what it's doing behind the scenes. So it needs to be able to allow that, even though it doesn't necessarily make sense to do it that way, and it can cause some problems. So this is just an example of where we have to be careful and make sure we dereference things with our star operator whenever we're using pointers, because 99 times out of 100, that's what we're needing to do. So we need to keep track of that. Okay. Now there are a couple of other ways of storing pointers and kind of going out there and creating them. So there's actually 3 ways. We looked at one where we put the star at the end of the data type when we declare our variable. So you're seeing here int space star space p count 1 as an example. This is valid. It is valid C++ code. It is not used very often. I've hardly ever seen it used. For the basic reason of it looks a lot like multiplication. So our star operator is used for multiplication, and when I have spaces on each side of it, I'm going to instantly think multiplication. That's not what I want. Okay, another example, and it is used a lot more than the last one, is to do your regular integer and then put your star before your variable name. I do see this quite a bit, and I see this a lot because if you look at our examples here where we're using star and then a pointer name, it's very consistent with that. Even though we're technically doing 2 things. In one case, we're telling it to define a data type in a certain way. The other is we're dereferencing that memory location. So even though they perform different things, I do see a lot of developers, they prefer to do it this way. Uh, that way they're always kind of thinking in their mind, okay, this is a pointer, I've got my star always goes right before my variable name. Because if I put my star at the end of my variable name, that does not work. Just as an FYI, feel free to go ahead and ask me how I know. I'll tell you, I've done it before, it just doesn't work. It likes to make your application blow up and not compile. Um, So some people will like to do it this way. It is a matter of preference. There is not a right or wrong way per se. I personally prefer using the way that I first showed you, attaching a star to the data type name. That's me. Attaching it to the front of your pointer variable also makes logical sense. I would never say anything about that. If you do have your data type space star space instance name, I might say something about it. While technically correct, it is a way to introduce errors into your code, because if you get used to seeing that, you could use their locations, and that's not good. Okay. Other things that you can do, and let me tell you another reason why I prefer to put the star on the data type name. Okay. If I do, here we have int star p count equals, and I can assign that memory reference right away. If I go and I run this, notice that the information gets assigned right here where I say star, or I say p count, I say star p count, and it works. Okay, so that's an obvious thing that works just as I expect it to. Now, if I come down here and I say star p count equals ampersand count, that won't work. In fact, you'll notice it gives you a little red squiggly line saying there's an error, because I'm trying to dereference my memory location, and I'm trying to, and which is going to be an integer, and then I'm trying to store a memory location into where an integer value is, and it's a collision. It doesn't work right. If I do int star or int space star p count like this, while this is technically correct, this on line 14 looks similar to this on line 18, which is incorrect and a real problem. So we don't want to do this. Okay. So just that's a big part of the reason why I prefer to say data type star colon done. Okay. It just reduces some of that confusion, reduces some of those little issues that you're going to run into as you're building out your applications. Okay. Before I move on, any questions with this kind of very simplistic, very high level look at our pointers and how that information is being referenced and stored? If you're okay, give me a thumbs up. Okay, I got a couple thumbs up. All right, let's move on then. When you're going through and doing these types of things and doing practice code on this, take your time. Number one suggestion I can give you: take your time, work through it, work slowly, go line by line, very methodically. I could get that word. Do it very methodically, and when you do that, you are a lot less likely to make mistakes, which is very important, because you don't want your frustration level getting high. You're more likely to catch those mistakes. And the good news is, especially if you're using like Visual Studio, you'll see it catching some of those errors. The other applications out there, I don't know how well they're going to be at catching stuff like that. It's one of the nice advantages to using something like an IDE. You can catch stuff in code before it goes to the compiler. All right, let's talk about defining a whole new type of data type for us. And you're probably going to go, wait a second, that's insane. And you're kind of correct, but you're also not. So let's look at what we're going to do. And saying defining a whole new data type might be a bit of a stretch. This is going to be more about defining a data type alias. So a data type alias is where instead of specifying an existing type name, we can use a new type name that is more meaningful to us. A good example where this gets used especially is, let's say I do a lot of programming in other languages. I say, you know what, I could just define it. I could define it with this variable name over here that I'm used to. This is the one I go to a lot. This is one I have the most experience with, or I can't redefine the data type name over here, so I'll redefine it in C++ and use the one that I'm used to over here. That way, you keep it all the same. A perfect example of this is, let's say I was doing a lot of coding for Microsoft Office in the VB script that they provide, or VBA, Visual Basic for Applications. They have a data type called integer, just like we have a data type called integer, except ours is int, theirs is integer. So I could define int as integer. And the way I just do it is I use the keyword typedef, my existing type name, and my new type name. So if I come over here, you notice I have int count equals 10. Well, I could also come over here and say integer count 2 equals 12. If I go and build my solution, you'll notice it does not give me an error. So I can use the old data type name. I can use my new data type name. All I have to do is typedef existing type is new type. Okay. And I could do other things too. I can, this is going to be integer 2. Notice here now integer doesn't work right. Why? Because that's integer 2, not integer. Okay, so it wasn't like it is an existing type inside of C++. No, was not that way at all. That was something we created. Okay. Another example, and this is where some people will go off and do this, is typedef int star, and then I'll say something like pint. So this way, instead of having to remember a star or having to do shift and the number key, do something weird like that, I have pint. Pint is a pointer of type integer. And if I came in here, I could do a count pint. If I build my solution, you're going to find that it's going to work. So I can do little things like this to reduce the chances of there being an issue. Excuse me. I can do things like this, reduce the chances of there being issues that I might run into later on. So this becomes a huge clarifying process. So instead of confusion, I work to find a methodology that clarifies what I'm doing so that it's easier to work with. I have this way which works, I have this way which is just a little more clear. Kind of like how I put a P in front of all my variable names. I want to make sure that whatever I'm doing, I'm trying to be as clear as I can be and as simple and obvious as I can be. That way, when I'm going through, I'm debugging my code or I'm coding it myself the first time, trying to avoid having to have bugs they have to track down and fix, or you want to call them, squash them or whatever. Being able to have those pointer variables is a huge benefit. So just kind of keep that in mind if you would. It's a good thing to be able to do stuff like that, especially if it's going to help keep things straight in your mind. How often is it used? It kind of depends. I don't remember having typedef when I started learning C++ 25 years ago. It might have been there. I just don't remember it. So you'll find a lot of people who don't use it because it either wasn't there in the older versions of C++, or because we learned from people who have been doing it for years and years before it had it. They didn't teach it to us and they didn't use it. So it just kind of depends upon how recent you are and what you're doing, and how you're being able to use that. So do keep that in mind as well. Okay. So that's just a couple of examples where you can have stuff like that. Make sure I didn't forget anything. Okay. So, yep. Okay. You can use a const with a pointer, but I do want to kind of warn you on that. All right. You might say, well, why would I do that? I got a little bit of sample code here. I'm just going to copy and paste, and I'm going to show you what's going to happen with this. Okay. So I have an x and y value. I'm assigning the values of px and py to the memory locations of x and y. It's kind of going through a whole process. If we run this is going to be pretty clear, I think. X is equal to 5, y is equal to 10. The memory address, or px, is this, FABC, and its value is 5. FAB0 is stored there at 10. I'm using my little star symbol there. Okay. Does everyone see what's going on there? Any questions with that? Should be straightforward, right? Okay. Just for simplicity's sake, I'm going to do this. That. Okay. I'm going to come down here and do this again a second time. I said, well, why am I going to do a second time? Glad you asked. I'm going to say px is equal to py. Now, before we actually go out and do this, I want to and run this. I want to kind of get your opinion. What do you think is going to happen? Okay, what do you think is going to happen? So feel free to unmute yourself if you want to kind of chime in. Take a minute to kind of stop and look at the code and try to work through what it's doing. If you need to, that's all fine. We saw what it did before. At X, it printed 5. At Y, it printed 10. And then PX, because it was assigned the memory location of X, it displayed that. And then we did star PX, it put 5 memory location for PY. And we did star PY, dereference it, got the value there, which is 10. But here I put PX equals PY. What do you think is going to happen when we do that? What do you think is going to print out the second time? Okay, don't everyone jump in at once. If you don't know, go ahead and I think there's like a question mark or something that you guys can put up there if you want to try that. And you say, hey, I just don't know.
I think it either is going to set the memory locations equal to each other, or just cause the entire thing to implode.
Okay, so we have two options. We have number one, which is the value at py is going to get stored into px, so that px and py are going to be at the same memory location. Is just rephrase it and make sure I understand what you're saying. Is that correct?
Um, Well, since it's calling px, that's just a variable representing the memory location itself, right?
Right. Mhm.
And you're setting that memory location equal to another memory location.
Right.
Now that I think about it more, I feel like imploding is more likely because you're trying to set two memory locations that are not equal to each other.
Okay.
But it's either that or somehow it's going to overwrite the other one's memory location until they share the memory location.
All right. Does anyone else want to chime in and give a thought, or uh, do we want to just run this and kind of see what happens? All right. I don't see anyone chiming in or unmuting themselves, so let's go ahead and run this, and then we'll talk about what happens. So I'm going to kind of pull this off to the side so you can kind of see the code and then see the values. We set x and y equal to 5 and 10 respectively. They have their own memory addresses. And then we say px equals py. And obviously it did not implode, so thank goodness for that. But it did do your other suggestion, Hunter. So we took the variable of px, which stores a memory location. And we said, nope, I want you to point to a different memory location. So px and py now have the same value. They point to the same memory location. Notice that the value of x did not change. We weren't changing the value of x. We were changing where pointer x pointed to. And since it was a valid memory location for it to point to, now when I say star px, since it equals the same thing as py, they give me both the same value if I just look at px and py, or if I look at star px and star py. So we took one pointer that was pointing here, one pointer that was pointing here, and we said, no, I want both my pointers to point to this location. And when both my pointers point to the same location, this does two things. The first thing it does is I obviously now am referencing the same memory location, so therefore I'm referencing the same value. Because I'm referencing the same value, if I use star px or star py and I change the value for one of those pointer variables, then the value stored at the other pointer variable is also updated. So I can have multiple pointers that point to the same memory location, and if I change the value of that memory location, then they all get updated. Let's verify this concept real quick. I'm going to once again come down here and just do a little copy paste magic. Okay, we're going to update and say y equals 12. Y equals 12 is this variable. Py is pointing to it. Px is equal to py, so they should both equal it. And they're just going to reference the value that's stored there. Okay. So this should kind of make sense. It's obvious if I update y, then my two pointers that point to that reference are obviously both going to be updated. Because of this, I can get into a little bit of trouble. Having multiple pointers that point to the same value location has its purposes. Do not get me wrong. There are many occasions where I actually do this on purpose. Usually it's going to be because I have a list of items and I need to know my current item and my first item, and they start off as being the same value. But my first one I never want to change. My second one I want to be able to change as I move through this list. And there's a specific instance of this, and it's called a linked list. And we will talk about this in a lot more detail in CISC 210, just as a little FYI. So in CIS 210, an introduction to data structures, we see where we will keep a pointer at the head of a list, and then when I start my current locations at the head, so the same value, but then I update one. This one should never change unless I cut the head off and I use a different head. And I may or may not do that, depending upon my application. I may never change that value of that head. It always stays the same. So I want to look real quick at how can I fix that issue. Well, it's very simple. I have a const keyword. We've seen this before. And I can come down here and specify const px and const py. If I say const px, const py, these are both now constants. And you'll see that on line 20, I get an error. Now, very, very important that you make this distinction. Specifying a constant for a pointer variable means that my pointer reference will not be able to update. But, big but, the value stored at that variable can update. So I'm not going to change. I'm not going to be able to change where I'm looking at in my memory location. I'm always going to look at the same location, but what's stored at that location can change. If I try to build this, I'm going to get an error because on line 20, I tried to change the value of my pointer variable. If I delete this out, my error is going to go away and I can run this and it's going to work just fine. But remember, the value stored at that pointer location can change. So even though I have const px and const py, and I could do one const and one not const, that's fine too. When I change the value of my variable y, it fully lets it go and do it. Okay, so the value stored at that memory location can change. It's just that the memory location itself, the pointer always points to that same spot, never changing it. And that's the const keyword in reference to pointers. Any questions on that? Sweet. All right, one other quick thing I want to show you. So there's a couple of things I can do. Const py, okay. Notice I'm doing a star py. This is the same effect as updating y. I dereference y with that star. Which means I can do star py equals star px. Dereference, get the value, store it in dereference, and put it in that value. Okay. Notice when I dereference px and store it into py, my memory the values change. Values change, but the memory location is still different. So I have two different variables with the same value stored at those pointer locations. Okay, so keeping track of what's a pointer versus what's the value stored at that pointer variable memory location, that's where some of the confusion can kind of get into play. Okay. Any questions on that? Do I need to go back over that at all? I want to make sure you feel semi-comfortable with it. There are, like I said, I put examples on here. You can copy and paste them in. You can change values. You can try a couple different things. Try to break them. I encourage you to try to break them. The more this is personal experience, the more I tried to break stuff and figure out what would and wouldn't work, the more it made sense. I went, aha, I understand what's going on now. So feel free to look at this. Feel free to kind of test and process and figure that out. That'll be very, very helpful to you. So I go through a process. I kind of show what's going on and what's going to give errors. Okay. And if you need something that has some more examples, feel free to let me know. I'll be more than happy to take this and just kind of explode it out with more examples of what's working, what's not working, and explanations as to why, to make sure you understand this as good as possible. All right. Last one will be done a few minutes early today, possibly. If so, great. If not, that's okay. And this is in passing pointers to a function. We've actually kind of seen this already. So here's an example where I have a swap function. And the book actually has, I think, 4 different ways to do a swap. It's like, oh my goodness. Okay. So to do a swap, I have to have another intermediary variable, a temp x, if you would, or an int temp, if you would. So I'm using temps here. And the reason why is if I have 2 glasses of drink, and I don't have them here in front of me, I have 1 bottle of water, 1 is not 2. But if I had 2 glasses of liquid, and I need to swap them, I said, oh no, this liquid should be in this glass, and this liquid should be in this glass. I can't just put them together and swap them, okay? I have to have a third one. I have to go, okay, let me take this one, pour it in here, then I can pour this one and pour it in here, then I take that temp one, pour it in there, and then I got my swap, okay? Variables in C++ work the exact same way. I can't just say x equals y equals x, and magically make it happen. I have to have that third temporary variable. You can see it here. Now, what you also might see is that I have int star, which means I'm looking at the memory address for it. So if I come here, I'm just going to kind of copy this whole thing so you can see it. If we go and run this, what do you mean there was errors? There weren't errors. One little mistake. Okay. I'll have to go back and fix that in the sample code. All right. So I have a pointer type int, they're x and y. Here I have x and y. Of course, remember, I could have called these anything I want. So just as a kind of a proof of concept, I'll call these all x1s and y1s. We're going to run this again. We'll do the exact same thing. Remember, variable names, oops, click on the actual thing. Variable names do not matter when I'm passing them to a function, okay? So I could have called these Bob and Fred. Would not have mattered. All right. So I have X, I have Y on 17 and 18. On line 20, I print out X, and then on 21, I print out Y. Here I have 5, I have 10, just as I expect. I call swap. It says I'm going to get the memory reference for this integer, memory reference for that variable, memory pointer for temp, and then I just move stuff around. And life is good. Yay. Okay, that's what I'm doing. Very, very simple. Now, I can tweak that just a little bit. And this is where it can get a lot more complicated. Okay. So once again, I'm passing in pointer references, but I'm passing them as a memory location. Because I'm passing them in as a memory location, then I need to reference the pointer to store this information. So I can dereference it because of the memory location. Make sense? No? That's okay. Let's try this one more time. On line 22, where I'm doing my swap, I am passing in a memory location. So instead of using this by a reference where it goes and figures it out by itself, it's looking at it as a pointer. Because it's a pointer or memory location, that means I need to dereference, which is why I have an int temp. I'm dereferencing x, dereferencing y, storing it x, dereferencing, or I'm taking temp, which is regular integer, and storing it into dereference of y. If I go and run this, you'll notice that it looks the same. Now, it looks the same, but it's not. So what's the big difference? Let's come over here. I'm going to swap these back and forth. I'm going to make a little bit of change to my CLs, just real quick. Okay. So I want you to notice what happened here and how this is happening differently. So remember, the previous example, we dereferenced. We got the memory address, we dereferenced it. In this example, if you notice, I have F770, that's X, and it gets the value of 5. And F764 gets the value of 10. Okay? Everyone keeping track of that? We have X and Y. Now, in this example, I call swap. I pass in pointers. I swap the pointer where the memory address is looking at. Now, I have X and Y. 70, it's 10. 64, 5. Same memory address. We swapped them. Does the same thing. Two different ways. This way is a lot simpler. A lot simpler. Okay, so we didn't like rearrange where memory addresses were or anything like that. By passing by reference and not having to do the pointer thing, it was a lot simpler. The book shows you 4 ways. I think all 4 ways are unnecessarily complicated. It doesn't mean they're not unnecessary. It's just they're unnecessarily complicated. So I prefer to use this methodology, and this is the reason why. Notice I don't have to keep track of a bunch of like, did I put stars and dereference? Did I remember put ampersands and reference that? I didn't have to do any of that. Okay, it was all taken care of for me. Made my life a lot simpler. Okay, one of the key things that we need to think about when we're programming, no matter what we're programming, it doesn't matter what language or anything like that, is simpler is usually better. Because simpler means that we're less likely to make mistakes. If we can understand what our code is doing, if we can make sure that it's being processed correctly, that's the important thing. Okay, not some big complicated process just to prove we can do it. When we try to get kind of fancy and tricky, that's where we sometimes get into problems. Now, simpler coding sometimes means that it's not as efficient, and we can go back in our code samples and say, okay, let me see, what's running more often, and I'll go and say, oh, I got this little piece right here that's running, every 30 seconds, and it takes 20 seconds to run. Let me see if I can optimize that. This thing over here, which isn't optimized at all, but only gets called once a day, forget it. I'm going to let it be handled, be slow. It's not worth it for me to spend the time optimizing and try to risk, for lack of a better term, messing something up. Okay, so I'm going to look at what's easy for me to process, what's easy for me to do, and what's going to be less likely for me to make mistakes, because mistakes are costly. They cost time to fix. They cost time in bad reviews that might cause people not to use their application. We want to avoid that. So we want to look at how can we do things that are simple and easy, and then if they are not efficient and we see our code running a lot of times, then we'll go and work on optimizing just those sections. But if I spent 10 minutes writing this little swap function versus 30 seconds, it's a big deal. As a developer, your time is worth something. And you can spend it writing a bunch of really efficient code, which hardly ever gets run, or just write a bunch of code and then figure out what needs to be optimized. Very rarely do you have to optimize everything. Very, very rarely. It's not to say never, but rarely. So look for how you can make your life easier just in the process of everything. Okay, that is all that I have right now for today. We're about 6 minutes early. We get done at 12:15. It's 12:09 according to my clock. Just real quick, are there any questions that you guys might have about anything we covered today? No questions from one. Like I said, this is a little bit complicated. If your mind goes swimming and maybe you need a day to kind of figure it out, that's cool. Go through some of my samples, see if you can figure out what works, see figure out how it breaks stuff and make it not work. Really help kind of dive into and make sense of all this. I have my office hours tomorrow morning. Feel free to join. And feel free to ask any questions as far as what we're going on in class or anything else. Anything that I don't know, I'll tell you I don't know, and I'll try to help. I know registration's been going on. If you have any questions on what's going to be offered next term, I'll try to look up and tell you best of my knowledge. I don't have all that info, but I'll try and give you the best info I can, and how to proceed from there just to kind of work with it. Otherwise, if you don't have any questions, feel free to have a good rest of your day. Thank you all for coming. I will see you all on Thursday. Like I said, unless you guys have questions, and then feel free to drop by anytime on Tuesday. I have both morning and afternoon office hours that you can stop by and ask questions. So, all right, I will talk to you all later.